right, we're going to continue with the day one notes. Now we're going to talk about adjacent arcs. Adjacent arcs are arcs of the same circle that have exactly one point in common. So on our picture here on the right, we can say that arc AC is adjacent to arc CD because they have they share a point, and that point is point C. So again, that was arc AC and arc CD are adjacent. Adjacent also means next to. And again, they share one point, only one point. The arc addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So in our picture on the right, we would say the measure of arc ACD is equal to the measure of arc AC plus the measure of arc CD. So in other words, yellow plus green would equal, what color do yellow and green make? Oh, they don't mix, that's right. But this big one right here, ACD. So similar to segment addition and angle addition, part plus part equals whole. This is a part, this is a part, and this from here to here is whole. Part plus part equals whole. Arc length. The distance along an arc measured in linear units. It is a fraction of the circumference. So to find the arc length, you can set up a proportion where you can say arc length divided by circumference is equal to x, which is the measure of the central angle, divided by 360. Or you could say arc length is equal to measure of central angle divided by 360 times circumference. Again, this is your circumference, 2 times pi times radius. And x stands for the measure of the central angle. A radian is the measure of a central angle, theta, and is the ratio of arc length to the radius of the circle. So again, radian, theta, is the ratio of arc length, so L, divided by the radius of the circle. Arc length divided by L, or radius. So a full revolution, a full distance around an entire circle, 360 degrees, is equal to 2 pi radians. (360 degrees) is equal to 2 pi radians. Half a circle, 180 degrees, is equal to pi radians. So that means 90 degrees is equal to half of that, which is pi divided by 2 radians. You'll use radians a whole lot more in Algebra 2 and Pre-Calculus, but we had to introduce it to you now just so that you are familiar with it when you get to those courses. The sector of a circle is a region bounded by two radii and their arc. So think of a sector as a pizza slice. So this entire slice formed by radii AP and BP form, form that sector in the yellow that I shaded. The area of a circle we talked about in the last unit. The formula for area of the circle is pi times radius squared. So the area is the amount of space that the circle covers, the total amount of space covered by the circle. And again, you find it by taking pi times your radius squared. The area of a circle, or sorry, the area of a sector is a fraction of the area of the whole circle. Because again, a sector is only a slice of the circle. It's not the entire circle, so it's just going to be that fraction. So to find the area of the sector, you divide the area of the sector by the area of the circle. Again, this is the area of a circle. Down here, this is the area of a sector. And again, it's equal to the measure of the central angle divided by 360. Or another way to look at it is take that fraction of 360 times the area of the circle. And we're about to practice this in just a moment, so please bear with me. A segment of a circle is the region bounded by the area of the sector, the arc and its chord. My circle is covering up my words. Region bounded by the arc and its chord. So if I were to draw chord AB on the picture, the segment we would be referring to is this section of space here. So to find the area of the segment, it's equal to the area of the sector, the whole slice, minus the area of the triangle. So it's like finding the area of the shaded portion only. We need the whole pizza slice, and then we're going to subtract the triangle to get that shaded portion. And there's a theorem that we must know. In the same circle, or in congruent circles, two minor arcs are congruent if and only if their central angles are congruent. So in other words, what that means is if I use the picture at the left, if angle 1 is congruent to angle 2, then arc FG is congruent to arc JH. And it can be read backwards as well. If arc FG is congruent to JH, then angle 1 is congruent to angle 2. That sounds like it should be pretty common sense, but this is just extra proof that it is written by law of a great power more greater than myself. But if the central angles are congruent, then the arcs are going to be congruent, and vice versa. If the arcs are congruent, then their central angles are congruent. And it can be on the same circle or it can be on congruent circles. It can work both ways. So for these examples, we're going to find the length of each arc and find the area of the sector formed by the arc and round our answers to the nearest hundred. So to find the length of the arc, the length of the arc is equal to the measure of the central angle divided by 360 times the circumference of the circle, which is 2 times pi times radius. So let's substitute what we know. The measure of the central angle is 57 degrees, and that is divided by 360 degrees. And we're going to multiply that times 2 times pi times our radius, which our radius is 3. And we're going to put it all in the calculator at one stop. So I would put it the angle part in fraction or in parentheses. So that's 57 divided by 360. And then times, so another set of parentheses, 2 pi 3. And the calculator knows to multiply all of those together. You don't have to use the multiplication symbol. So the length of the arc is approximately 2.98 when rounding to the nearest hundredths. So about 2.98. Inches. Now to find the area of the shaded portion, or the portion formed by arc CE. So to find the area, again, it's the measure of the central angle divided by 360 times the area of the circle, which the area formula is pi times radius squared. So let's substitute what we know. Again, the central angle is 57 over 360 times pi times radius, which is 3 again, squared. So now we're going to grab the calculator. Again, so it's 57 divided by 360 times pi times 3 squared. And the area of the sector is approximately 4.48 inches squared. That's its area. 4.48 inches squared. Now for the final example, we're going to use the same formulas, but we're looking for a QR. If you notice, QR doesn't have a central angle measure, so you have to find it first. And that's probably the only tricky part on this one. So the central angle, we know the rest of the circle is at 112 and 130. And this angle, QPR, is vertical to this angle, STP. Oh, no, they're not. They're not vertical. Okay, rewind. Let's say that you know that RT is the diameter because it goes from edge to edge and through the center. It's a straight line. So that means that this arc here, RQT, is a semicircle measuring exactly 180 degrees. So I know that I have 112 of it, so I can find the remaining portion by taking 112 minus, or 180 minus 112. So let's do that. So 180 minus 112 would give us the measure of QPR. So that would give us 68 degrees. So the measure of QPR is 68 degrees. So this is 68. Now that we know what that measures, you can answer the rest of the questions, finding the length of the arc as well as the area of the sector. So please complete this part on your own. And this concludes your notes for today.